Concrete literally builds our world, but hidden inside every single one of those structures is an unsung hero and a secret set of rules. Today, we're going to decode that hidden language that keeps our city standing strong.
I mean, you've seen it, right? A concrete structure slowly rising, and there's this really intricate web of steel bars inside before any concrete gets poured. It looks complex, and, well, it is. But what is it really doing? Why can't we just use concrete on its own? That question, right there, leads us straight to concrete's one big secret, its fatal flaw.
You see, for all its incredible strength, the most common building material on the entire planet has one critical weakness. And understanding this weakness is the key to, well, understanding pretty much all of modern construction.
Okay, let's break this down. Concrete is an absolute champion when it comes to compression, that squishing force. You can squeeze it and it just holds up, no problem. But the moment you try to stretch it or bend it, that's called tension, it's as brittle as a cracker. It just snaps, poof. And in a world where buildings need to flex and sway a little, that's a huge, huge problem.
So if concrete can't handle being stretched, what can? Well, let's introduce the hero of our story, reinforcing steel, or as everyone in the industry calls it, rebar.
Rebar is specifically designed to do the one thing that concrete just can't. It is fantastic in tension. So, by embedding these steel bars inside the concrete, we create this amazing team-up, a material that has the best of both worlds. The concrete takes all the squishing, and the steel handles all the stretching. It's kind of like a body, right? The concrete is the solid mass, but the rebar acts like the tendons, giving it that flexible, unbreakable strength.
But here's the thing, not all rebar is created equal. Nope. According to engineering standards, like India's IS 1786, there are different grades. You've got your basic, smooth, mild steel, which is often just used for secondary stuff, like the little ties that hold the main bars in place. But for the real heavy lifting, the main structural work, engineers use what are called high-strength deformed bars. And that word, deformed, is way more important than it sounds.
Deformed just means the bar isn't smooth. It has all these ribs and ridges along its surface. And those ribs are the absolute key. They create a powerful mechanical bond. They literally lock the steel into the concrete around it. So when a stretching force hits, the bar can't just slip out. It holds on tight, and it transfers that stress safely through the whole structure.
So we know we need that ribbed steel inside our concrete. Okay, cool. But you can't just throw it in there and call it a day. Where you put it, how you protect it, and how you connect it is all governed by a very precise and absolutely critical set of rules.
Our guide for all this is a classic engineering handbook from the Bureau of Indian Standards, all the way back from 1987. And its foreword says it all. Detailing, that's the precise drawing and placement of every single bar, it's not an afterthought. It's where the design actually becomes reality. It's where safety is truly built.
Now, this handbook is hundreds of pages long, full of really complex charts and diagrams. But what are the core principles? What are the absolute non-negotiables that every single engineer and builder has to live by?
Well, we've boiled that whole complex rulebook down into 3 golden rules. If you can understand these, you'll understand the hidden science that's keeping our buildings safe right now. Okay, first up, the rule that's all about protecting the steel itself. And it's actually pretty simple. Give it space. This is known as the rule of concrete cover. It's all about making sure there's enough protective concrete between the rebar and the outside world.
So why does this matter so much? Well, first, it protects the steel from moisture and air, which is what causes rust. And rusted steel expands, which can literally crack the concrete from the inside out. Secondly, it insulates the steel from fire. Steel loses its strength when it gets too hot, so that concrete layer is like a protective blanket. The handbook specifies clear minimums for this. For a beam, that rebar needs at least 25 millimeters of cover. For a column, it's 40. This is a non-negotiable shield.
All right, let's move on to our second golden rule. This one is all about making sure the rebar can actually do its job.
We're calling this one, Get a Good Grip. Officially, it's known as the Rule of Development Length, and it tells you exactly how deep a bar has to be embedded into the concrete to properly anchor itself. Think of it like this. If you're tying a knot, you need enough string inside the knot for it to hold, right? If the tail end is too short, it'll just pull right out when you yank on it. Development length is the exact same idea for rebar. It's the absolute minimum length needed to make sure the bar can take its full design load without ever pulling out of the concrete. It's all about creating that unbreakable grip.
And that brings us to our final golden rule, which solves a really practical problem that happens on every single construction site.
We'll call it pass the baton. This is the rule of splicing. You see, steel rebar doesn't come in infinitely long pieces, so to build a tall column or a super long beam, you have to join shorter bars together to make them continuous.
The most common way to do this is called a lap splice, and it works just like a relay race. The baton is the tension force that's traveling through the steel. To pass it from one bar to the next, you have to overlap them. The rules dictate the exact length of that overlap, and, this is critical, you have to stagger these splices. You never, ever want all your connections in the same spot, creating one big weak point. It's all about making a seamless transfer of force.
So concrete cover, development length, and splicing. These aren't just technical details for engineers. They are the fundamental principles that shape the world that we all live in.
These rules, they are not suggestions. They're the invisible engineering that ensures our safety every single day. Getting this detailing right is the difference between a bridge or a building that serves its community for 100 years and one that fails under pressure. It's a hidden code of safety, written in steel and concrete.
So, the next time you walk into a concrete building, just for a second, remember that hidden steel skeleton inside, meticulously placed according to these rules, silently holding everything together over your head. I promise you'll never look at a concrete wall the same way again.